Thanks, Magenta. I'm glad you guys gave me a microphone. I naturally have a very soft voice, so if I need to speak up, I'll see people leaning in. So I'm Karen Yuen, and I'm from the Jet Propulsion Laboratory. I am currently the Science Data Applications Lead for the Orbiting Carbon Observatory 2 mission, and I'm also NASA's Deputy Program Associate for OCO3, that's the Orbiting Carbon Observatory 3 mission that will be going on ISS. And we are planned for a launch in February 1st, 2019. And so I'm going to talk to you today about a perspective from space. Obviously, with NASA, everything is about space. And this image should tell you a lot. This should be a very recognizable planet for most people, I hope. And so I wanted to talk about this. So what is NASA? I think those of you who are fans of NASA or are aware of NASA, these images should seem very familiar to you. Most of what we do, people think about when we go to Mars, when we go to the outer planets, obviously the incredible work that we've done on Hubble. Astronauts, I don't know, I dreamed about being an astronaut, and the international collaboration that we've done right now on the International Space Station. These are all very iconic images and associations for NASA. But what I do is we look at planet Earth. And I'm just show of hands, how many people realize that NASA was studying Earth science? Okay. That's not fair. So one of the reasons I put this talk together was that all too often people think about NASA, they ask about astronauts, they ask about Mars, they almost never ask me about Earth science or planet Earth. And in fact, a funny story, I was going for a science team meeting at Boulder, and I was at the Denver International Airport going to pick up my car, and we get discounts if you say which company you work with, and the gal asked me for my badge for identification, and she said, "Who do you work for?" And I said, "NASA," and she actually said, "How do you spell that?" And so I really thought, wow, we've fallen so far. So I'm ready to talk to you about Earth science and why Earth. And most of you should be aware of this already, so I'm going to show you a little animation. This should look familiar to folks. This is just a small sampling of the constellation of satellites that we are currently flying. There's a lot more. This animation was done a while back. We need to update it. I wanted to show this because every single one of these satellites have at least one or more instruments that are tuned to do something very, very specific. And I had a wonderful colleague years ago that described it so well. He called our satellites eyes in the sky. And what we're doing is remote sensing. We're seeing something from afar. Everything we're doing right now, everything that you are experiencing is being remote sensed. Looking at this, you're not touching it, you're seeing it. You're gathering the data and you're making your own interpretations and your own decisions or whatnot about it. We do this every single day of our lives. We do this the moment we wake up. And so people forget that using satellites to make these observations is actually a very, very natural part of who we are and how we do things. And it gives us an ability that that goes beyond what we're capable of. If you think about it, you know, we're remote sensing right now. Those that are in another room can't see me, but they can hear me. That's being remote sense, right? And then when you wake up in the morning and you're desperately looking for that coffee, you smell the coffee first before you get to taste the coffee. That's remote sense, and you know that. So that's something that's very, very important. So you think about all of these satellites and the instruments that are flying, they are tuned to look at different parts of the electromagnetic spectrum, and they're able to see the Earth in ways that we can't see with our own eyes. And if you guys remember in grammar school or middle school, when we learned about the electromagnetic spectrum, what we're able to see in the visible light is in really, really, really small, which means that we're very bad sensors. We can't do a lot, but we can build instruments that can look at other parts, and we're able to see incredible things. So why space? Why are we looking at space? Well, first, I wanted to show you this updated picture. Like I said, we didn't have a new animation. This shows you the constellation that is planned. All of this is in lower Earth orbit, LEO, and we are, some of them are already flying, some will be launching soon, some are in the plan. So you can see that there is a lot of investment by the United States in maintaining this constellation of satellites, maintaining this capability for us to keep on studying planet Earth. But why are we doing this? Well, first and foremost, it is the unique vantage point of space. If you go out into space, you're able to look at the planet as an entire system. And if you recall, in science, when we study open systems and closed systems, the Earth is a closed system that we're able to finally make that true observation from afar, from space. But we're also able to see effects that we cannot do from the ground. And I'll take today as an example. We've had a heat wave, okay? It's been incredibly hot. You're aware of it, and you go out and you're like, oh God, it's so hot. And so in your head, people are leaping to things saying, well, that's just proof of global warming. They say it must be global warming because it's warm outside, but that's how we relate to things. And then if you think about what happened last winter, when there were all these incredible snowstorms and these record snowstorms, and there were a lot of people on the East Coast that were saying, oh, where's that global warming? Really, this is not happening. But that's how people remember things, and that's how we relate. We relate just geographically, and then we make these leaps and assumptions psychologically because it's what we have sensed, it's what we're used to, and it's what we have accepted. And I like to think that we provide a true neutral platform. It's a fact-based platform. We're flying from space, we're gathering the data, we're making the observation in a way and providing the data for free so that people cannot make these assumptions. And that's something that we're incredibly proud of. And aside the geographical and psychological borders, there's obviously the political borders. When you observe from space, there are areas that we cannot get to for whatever reason. And it's no surprise that most of our sensors are in the Northern Hemisphere. Northern Hemisphere because we have more people living in the Northern Hemisphere than they do in the Southern Hemisphere, so they can put the sensors there, they can maintain it. We don't have a lot of measurements in the Southern Hemisphere. By having remote sensing capability from space, we're able to make those observations and also over the oceans. So what can we see with everything? I just put up a sample of some images that represents what we can really do with remote sense data and imagery. Just so you know, most of what we do are not pictures. We don't put out, we don't really fly optical instruments anymore where we're taking pictures. But I wanted to show some examples of that. So my mission that I work on is this one right here. That's the OCO2, Orbiting Carbon Observatory 2. And I love my mission. Just so you know, it's been almost a lifetime of work. You have to understand, I started at JPL relatively young, 2001, new mom, just this project took me in, and I started working on the phase 2 of the proposal, and now we're working on OCO3. So it's almost like a child. And what's incredible about this particular mission is you're aware of all the concerns that we have about atmospheric CO2. We're looking at it from all the ground sensors. OCO2 was designed and built to fly from space, and we actually have a precision that is absolutely extraordinary. And it's extraordinary because if you take any sort of ground sensor, and I know there are a couple guys who are residents here and we're talking about sensors, we have validated our data to be within 0.5 to 1 parts per million from space relative to the ground sensors. That's how good it is right now, and we're able to get that coverage. This is a global coverage that we get. We sampled the Earth, and this is a 16-day coverage that we're able to achieve. And as you can see, we're getting areas over the oceans, we're getting areas in the Amazon, Australia, places that we really didn't have sensors before. I don't know if you're familiar with this. There was a launch recently of GRACE follow-on. GRACE is a mission that actually measures gravity. And we can pick that up because we can pick up we use the gravity to determine the mass changes that are happening on the planet. I hope this is an iconic image for folks. If you're familiar with El Nino, this was pretty much the first time we were able to give a picture from space of what El Nino looks like. And this past year, a group of us actually were able to put out some papers that we're very proud of that got accepted into Science. And we were able to combine some of the data from OCO2 and other NASA instruments where we were able to show what was happening without the 2015-2016 El Nino. And I want to point out, we're very much used to El Nino being about lots of rain. If you remember people talking about the Godzilla storms and all that. Once again, this is what's happening in our backyard. There are other things that are happening elsewhere in the world, and we're not aware or been told, if you will, if we look at the media, all the devastation that's happening elsewhere in the world with very devastating droughts. You know, we get all the rain, somebody else isn't getting it, and there are consequences for that. And then above is an image of hurricanes. So if you think about, you learn about all these hurricanes and you learn about the satellite data, it is the advent of the instruments that are developed that allow us to have that capability to show when a trajectory or a path changes from the satellite, because we can't see it from the ground. And being able to see how a hurricane feeds, if you look at that particular image and you see the warm colors, that's where you have the most energy. And it makes sense because a hurricane is fed by the oceans, that's the fuel source. And as it crosses over land, it loses that energy. And so you see the color change, the color change, you'll see some of that. And then over here is another mission I had worked on, which is the Soil Moisture Active Passive mission. And we're able to look at flooding because we have both a radar and a radiometer. Right now it's just the radiometer that's working, but we're able to see the wetness of a soil, the moisture that's in the soil, the water content, because as I hope you know, water has a very high heat capacity. And so we're able to pick up information through the dielectric constant. And that's how SMAP works. And then I've got a couple pretty images there that just remind us how beautiful this planet is. If you've looked at if you go hiking and you're able to see some of the alluvial fans, we're able to see that from space, and it's just gorgeous. And this is one of my all-time favorite images from an instrument called ASTER on Terra, one of our, the flagship mission on the Earth Observation System, EOS. Can anyone guess what that image is? Where do you think it is? Sorry? No, it's not Yellowstone, but you're in the right direction. It's actually a part of the mountains that are in North Africa. And they were able to zoom in on that. It's the Anti-Atlas Mountains near Morocco. And the different colors you see is because of the thermal band that they were able to differentiate the different rocks that you can see. So they were able to show that the swirls is because with mountains, as you know, with the plates, they get crushed and they change direction. So this is millions of years being formed and all the different rocks that you have that's forming. And I just always thought that was just... Did I break it? Shit, sorry. He told me not to do that, and I did it. Sorry about that. Okay. Yeah, but he told me. I'm sorry. But for those of you who are sleeping, you just woke up, so... So that's another idea. That would make a good alarm clock. Okay, and so with all this information, who's using this data? That's a question I ask because I do science data applications. What does science data applications mean? I'm not a part of the science team. I work with the science team. And NASA has this very interesting way of putting out data that's very hard to work with, and we focus on a very small group of people. Don't laugh, you know it's true. And so we actually have to justify. We tell everybody, you have free data, come work with our data. And then people go in and they pick up the phone or they email me and they're like, what am I looking at? How do I do this? I can't even download anything. So that's why I have a job. But so our data, the primary users of our data would be our chosen science team and academia, people that are way smarter than me in what they do, and they're just like, they are the world experts in the fields that they're working in. And we also work with some of the other federal agencies, and those are some of the folks I work with. For example, my work on OCO2, I work with the different agencies within the USDA, that's the Department of Agriculture, which includes the Agricultural Research Services and the US Forest Services. And then NSF, obviously, for research. We also have international partners that we work with. They often work with us to build, we'll build the hardware in-house or collaborate with them in different parts of the instruments, and they may provide a launch vehicle or the bus, whatnot, and they work with us on that. And as of more recently, there are large corporations that are also interested in using our data, and just those of you who are interested in Google Earth, for example, where do you think all the satellite data started with? So that's where you get that. So bear with me, I know there's a lot here, and I think I'm doing okay on time, right? Okay. I'm gonna go through this. I'd be happy to go through this in more detail with folks. This is one of those charts that I can talk a long time about it, but I'm not. I'm gonna. This is just to walk you through the process a little bit of how the data is used. So we have this lovely image of an artist rendition of the OCO2 satellite flying right now. OCO2 launched back on July 2nd of 2014. And it was a very, very exciting time for us because after we lost OCO, it was absolutely devastating. And it was one of those moments where I truly didn't know what to do because I was at Vandenberg Air Force Base. I was still on base when I found out that we had lost the satellite. And I just remember that long bus ride back to the hotel and thinking like, oh God, what are we gonna do now? And, but we were able to take flight spares. Yes? Yes, it was a launch failure. I think this is being recorded, so I'm gonna be nice. So we had an issue. The original launch vehicle was a Taurus XL from Orbital. And unfortunately, we had an issue with the fairing. So if you know about the fairing is where the observatory would come out. And the way the design is it's like a clamshell. So it's supposed to open up. There's it's a two-part. So there's actually a gas that would force it out. So there's like a mini explosion to push it out. But there's also the latch that opens for the clamshell. And what had happened was the clamshell failed to open. So when you get to a certain altitude, it was too heavy. So we changed the trajectory, and it actually started going back down, and it crashed into the coast of the Antarctic Ocean. That's another thing we do. We launch out of Vandenberg for the polar orbits. We launch out of Vandenberg because as we are climbing up to altitude, we really want to be over as unpopulated waters as possible. So you see that. And then nobody thought anything of it. They just said, okay, it was unfortunate. This happens. We had a disaster. And then NASA had actually used that same launch vehicle for another mission, but it wasn't a single-strand instrument like ours. There were multiple instruments on it. It was called Glory, and the exact same thing happened. So they lost 2 missions. And I remember getting up in the morning, and my project manager and others, we were texting each other. And when they lost Glory, we were all just like, it was really like, oh my God, it's happening again. And I remember my project manager then, Ralph, he actually called up the project manager and said, I can actually say I know exactly how you're feeling. You know. So yeah, that's how we lost it. But just to give you a quick idea of how OCO2 works, we were able to superimpose our footprint over a city so you can get an idea of what we look like. It's about a 10-kilometer swath. I like to point out that OCO2 doesn't map. We do global coverage, but we're a sample mission, so we have a 10-kilometer swath, and we get lots of data over that skinny path, and we make multiple paths throughout the day. But we can't see through clouds, because we have to go through sunlight, which means, and last time, I'm sure all of you check when you look at anything from ISS, we're not exactly a cloud-free planet. So it makes it very difficult to gather data, so we don't say, even though we cover the Earth multiple times over the Earth, we make 14.5 orbits a day, we really have to say that we truly cover the Earth statistically about every 16 days because we have to take out all the bad pixels and cloud images and things like that. And so that's the footprint. And then our beautiful product that we get is the spectra. I don't know if folks are fans of spectra. That's what it looks like. People who love spectra, we look at it and it's like, oh my God, that's gorgeous. Look at the absorption, that's amazing. Look how clean it is. And then you go and you show it to people and they're like, what am I looking at? So OCO2 and eventually OCO3, it's the same instrument. We operate on, we're a grading spectrometer, and we have 3 channels that we look at. We have an oxygen A band and 2 channels that look at the carbon dioxide, which would be the weak CO2 and the strong CO2. The difference between the strong and the weak is that one is a little bit better at screening out the aerosols and the clouds. And we have the oxygen because that's our constant that we use, because the amount of oxygen in the atmosphere is relatively constant. So we actually, when we make our measurements, that's how we can quantify things in the concentration. And we take the information from the spectra and we actually put it into a format that's relatively easy to understand, as in values, and those values can then be translated and put into global images such as these. And these are great to look at. They're important. We can make animations with it. But those values are really at the heart of what the science is being done. And the science that come from this, we're just starting. And I'm so excited about this. My colleague Jinji, this is the leading paper that came out in Science. And she looked at the 2015-2016 El Nino. So in a snapshot, she told the story. When we were experiencing the storms and the rain, there were massive droughts that were happening on 3 different continents for 3 different reasons. And because of OCO2 data and MODIS data, so we combined the data sets, she was able to point out that it was actually the driest it's been in 30 years. And so we also saw a marked decrease in photosynthesis. So if you think about the normal methods that we use to maintain a balance of atmospheric carbon dioxide, the sources and sinks, they weren't working the way they were supposed to be working. The sinks, the plants that were supposed to take it up, they weren't working. And since it was dry, it exasperated things, so our sink was gone. So all of a sudden then they're not taking in the CO2, so we're actually maintaining more CO2 in the atmosphere. And similar thing was happening in Africa. It was hotter than normal, and what happened was that there's a lot of dead materials and decaying materials that there are around the areas they were looking at, and because it was so dry, what happened was they started becoming a source. They became a carbon source because of the decay. And then the third thing that happened, if you're aware of what's happening in Indonesia and other parts of Southeast Asia, we actually have a lot of, they're doing a lot of deforestation and clearing for agriculture purposes. And they went out of control because it was so incredibly dry. There, it was the second driest time that's been in 30 years, and because of the burning that they were doing, it got out of hand. And so the biomass burning became another source of CO2. Not only were we not able to take up as much CO2 as we were normally doing on an annual basis, we were actually putting more in the atmosphere. And she was able to quantify the amounts coming from those 3 different continents. And the total amount, basically what happened was during the 2015-2016 time frame, we had the largest increase of CO2 back into the atmosphere that we've ever had in human history. And that was largely driven by this event. So, and that's significant. That's a large reason why it was the leading paper in science. And, but I wanted to show you this animation very quickly. I hope this is familiar with folks. If you're fans of Google Earth or you look at any of that, you'll see this sort of image, and we call this the Earth breathing. I'm showing this because it's not our data, it's MODIS. Our satellite's able to pick up when there's a greening. And so that's why we call it breathing, because through an annual process, you'll be able to see areas. See, now we're greening, so that's spring, summer, now the senescence, and so it's fall and winter. And we're able to see the seasonal variations over time and the areas. And it's really cool, because it's really like looking at the planet breathing. And the process for green, for vegetation, would be from photosynthesis. And we've been able to observe this for decades. And we do this through the Normalized Difference Vegetation Index, or NDVI. It is the standard that we use to look at vegetational changes. Why am I bringing this up right now? OCO2 was designed to look at our primary science objective is to look at atmospheric CO2, and we want to be able to measure it at a very strong precision, like I had indicated, which was originally 1 to 2 parts per million, and we've done better. However, if you recall, we have 3 channels. And one of the channels that we look at, the oxygen A band, that was supposed to be our constant, we're actually able to pick up in the spectral range solar-induced chlorophyll fluorescence. Does anyone know what that is? You know, I do have fellow JPLers in the audience. So solar-induced chlorophyll fluorescence stands for SIF. And basically, those of you remember, once again, going back to grammar school and middle school, when we talk about photosynthesis, you know what happens with photosynthesis. You have sunlight, and the plants and the chloroplast, they basically turn it into sugar, right? That's how they feed themselves. That's the energy. There's a little bit more to the process when they're using the photochemistry. That's when they turn their food and they turn into sugar. There's also a part where they lose some of that energy from heat. They also do something that's called photochemical quenching. And the fourth thing that they do is actually where they re-emit the energy from a photon, because you're going from an excited state to a less excited state. So you're losing that energy. And with that photon emission, what's happening is that it's light, it's fluorescence. That's essentially what it is. And what happens is that the more photosynthesis, the more active it is, the more of these photons would be shooting off. So we're able to see this from space. And why is this important? Because it represents a physical measurement of what's going on with photosynthesis. And that is in lieu of what we see here, which is greening. For those of you who have houseplants, you know how it is. You have your houseplant, you hopefully water it every few days, once a week. Usually you water it because it starts turning brown. And you're like, oh crap, I need to put some water in. So that gives it about a week or something like that, and you're like, ooh, I gotta do something about this. That's what this is. We see when something changes colors. You know, so when it's saturated, when it's green, we just assume everything is fine. But we don't know if a plant is stressed. We don't know if they're lacking water, if there's heat. We don't know because the color hasn't changed. It takes a few days for it to catch up. With SIF, we're able to learn within hours if something happens, because the plants turn, the stomatas, they close them to conserve energy. And we're actually able to pick that up because we'll see a marked decrease in the photosynthetic activity. Now, there are obviously limitations. We're doing this from space. We're not doing this coverage everywhere, but we're able to give more information than a lot of the existing sensors, and we're actually a good complement for a lot of the ground sensors that exist right now. So I want to show you, I know it's not as pretty, but I want to show you that this is an image that was created back at a workshop at Caltech that illustrates what we're doing with SIF, which is you have the chloroplast. That's where you see the sunlight coming in. We're literally measuring at the different levels that we could look at SIF, from the chloroplast to the leaf level. Right now, for us to determine SIF, we go out in the field and we actually have spectrometers, if you will, that we have handheld that we applied to a leaf. We have a condition where we mimic when there's no light, and then when we turn the light on, how it's measured, and it's very, very laborious. And I was on a field campaign, and we were out there where folks have the instrument, and you're literally bent over, because we were looking at soybean and corn, and we were literally clamping leaves. And you take plots. And trust me, when it's hot and humid out, it's not fun. Whereas if you can look at it from space, we get a lot more information. And in fact, if I didn't mention this, most of the instruments that we build, that we fly in space, we actually test out flying on aircrafts. And we also continue to do that for validation purposes. So you can kind of see that suite where from leaf to a single plot to airborne to space. What do you mean by wavelength? Well, there's a range, okay? So the range is about 650 to 800, and we're looking at about 757 to 770. So those are the, nanometers. Those are the two areas that fit into what we can look at in our spectral, the channels. It's stronger in the 600s, but you would have to build something exclusive for that. It was a very serendipitous measurement for us because we built it to look at CO2, and then we happen to be able to see signatures in there because it's noisy. I'm going to admit it, you have to tease a lot of it out, but we were still able to, and get great data from that. And let me show this. Give me a second. So this is straight from our level 3 product that Christian processes, and we're able to just pull this straight from Panoply and make these images ourselves. So in real time, you'll be able to get a lot of information. So yes, the other one's a lot prettier, but this is actually what is going on. This is the physical measurement. So, eventually we'll be able to make it prettier, but it's not bad when you just put the data in and you can open it up and start playing it as an animation. That's something that we're able to do over time. And as you can see, we have a scale of the amount of absorption. So the higher the number that you get here, the more active the photosynthesis was. And let's see. So I wanted to end by showing this slide from the recently released decadal study from the National Academy of Sciences. They do a decadal survey every 10 years. And they basically put into motion what the plans are for the future, for the instruments that we should be building, the satellites that we should be flying. And I wanted to end on this note. There's this realization that all this wonderful science data is not just gee whiz, that there is a real need for it, and there's a lot of applications that can be developed. We're limited in our capability. We have a need to understand more, and there's a reliance more and more on using the satellite-based remote sensing capability to help us do our work. As a matter of fact, my colleagues at USDA, Congress put that into what they're doing because of the limits in budget. They really want them to start doing, not in lieu of their intensive surveys that they do, but they really want to have some more complements where they rely and start using more remote sensing data. So that's a great opportunity for us to work with them. But you can see that there's just areas that haven't even been discovered of what we can do with remote sensing data. And I like to point out that's your tax dollars at work. So it's actually something that's beneficial. Obviously, water quality, that's very important, and availability, knowing where that out with the massive droughts that we've had. Natural disasters, that's another area that is of concern. I'm not going to talk about the keeping us secure. Sorry, I don't, whatever. The health, we're able to, some of our sensors, we're able to do the tracking of vector-borne diseases, with mosquitoes. That's something that's very important. And people have theories about what might be affecting that. Are viruses being carried on dust? What does it all mean? So that's a very exciting area. My area that I'm looking into right now is using our SIF products to actually look at some of the invasive species in different parts and plots and forests, and be able to have that capability, because currently most of my colleagues, they're only able to do their extensive surveys because of the budget they have about every 5, if they're lucky 5, but 7 years. And if we can provide more information to them as where the infestations are, and this is all still very researchy, but it's kind of a neat application that we could do for a larger area, and we have all the information across the country. And obviously continuing the weather satellite, because we have to get up every morning, and that's the first thing we do, isn't it? We check the weather. Should I wear something light or not? But I want to end by sharing this chart with you, but also to give, maybe you guys don't need the reminder, but I always tell folks that there's a lot more to NASA, and we might be doing a lot of exploration out there, but don't forget that we're also exploring our own home planet. Thank you. Questions? Okay. Should I? Oh, okay.
Okay, you already walked over there.
Hi. Is there any relevant information coming from the oceans on that breathing of the Earth also to be measured? I don't know, algae respiration?
Oh, yeah, I just didn't cover it because that's not my area of expertise. There's, I would say oceans, especially for JPL, we actually have the physical oceanography DAC, that's the data library, that's actually housed at JPL. So I would say that we have some of the world experts and data users of oceans there, and almost anything you want to look at, they can look at. They look at algae blooms, they look at fluorescence, they look at sea surface height, sea surface temperature, because they put it into the models.
So there's a complementary animation or data set to this animation that you played.
Yeah, this is all land.
This is all land.
Yeah,
right.
my focus is not just strictly land. On the ocean side, there's just a whole community and other sensors. If you've heard of CWIF, since they look at the ocean color, a lot of neat stuff being done there.
Cool,
yeah.
Thanks.
Perhaps it's not comfortable for you to answer this, but the present administration, the White House, is not in favor of climate science, and I'm wondering how that's affecting your funding.
How it's affected our funding?
Yes.
That's one thing I've learned over time. I've actually worked at JPL long enough that I've worked through 3 different presidents. I'm counting the present one, 3 different presidents. And the interesting thing is that the president, when he comes out with his budget in January, there's a lot of news and fanfare about it, and they'll say, oh, this is good, this isn't bad, he doesn't like this, he doesn't like that. But what really comes down to it is that what does Congress actually pass as a budget? And for as long as I have been at JPL, we've been on a continuing resolution for every time until this past spring, where we actually passed a budget. And despite some, yes, he's not going to change his rhetoric and how he views on things, but we actually benefited because OCO3 was on the chopping block, and Congress put the money back in, and we actually got, when they gave us the launch vehicle, that was all our, what's Mike Freilich's title? I forgot. So he's the head guy at Earth Science at NASA. I forgot, he's the head. I forgot the exact title. That's all he needed in the language was like, oh, okay, launch vehicle, you guys are good to go. Because we literally, you know, we're in thermal vac right now, so, but we'll be done and we'll be ready to go. So yeah, it creates a lot of noise, but I can say something that was really, really cool that happened. So we have a new associate administrator, and Bartelstein, being from Oklahoma, has always said, oh, you know, climate, because it's oil country, and they're like, oh, we don't want this. He's actually changed his mind, and he's come forth during our all hands and stated that you guys have changed my mind. So there's hope.
Yeah, you said something about oxygen stays the same and the carbon changes?
Oh, okay. Okay. So OCO2 makes a measurement. So if you can imagine, I was talking about the 10-kilometer swath. So at any given point when we're flying, we fly at the same time every day. But we make certain crosses at 1:30, okay, 1:30 p.m. And basically, OCO2 is a column. We make them, so imagine this as a sensor. We get information from the space down to the ground. So we get all the information that's within this one column, right? So when we actually have the algorithm, we have to look at what's within this particular column. So where are the variations? We expect the CO2 to vary because of the places that we look at, but we need to have something constant and that's where we mean, because it's relatively, there's a whole bunch of nitrogen. We're not worried about that because there's so much of it. So we use oxygen as the constant for the concentration.
So why does the oxygen stay the same? I mean, how can you use that as your reference? It's complex.
It is, but it's all relative. So it's there you go. It was well mixed and then relatively, yes, compared.
But
yeah.
The carbon dioxide is changing. Doesn't the oxygen change too?
Not to the same degree, no. So I'm sure there's more. I would have to talk to Dave Crisp. Dave would be better at explaining that because they designed that. I don't know, I'm sorry.
Okay.
Any other questions? I thought it was really interesting how you talked about being able to track from space places that didn't have ground sensors, particularly in the global south. And I'm wondering, looking at this last slide, the ways in which I work in public health, and I'm wondering in which ways or how the priorities or use cases for how this data is being used in a lot of the drought-related or economic-related public health soon-to-be disasters or avoidable disasters around the impact of climate change. And if you have similar partners as you do with sort of earth science, or if that's being translated into other arenas.
When you say other arenas, do you mean like other parts of NASA or other agencies?
Sort of like you were talking about partnerships or not partnerships, but combined research where your data was being used to support real changes in the earth science. Has this data been used in economic or public health with the World Health Organization or the Yuen? I know that the World Health Organization has drought and climate change as one of its core sustainable development goals, and I'm curious if you have any insight into sort of how this translates to that realm.
Those are the bigger
sorry,
goals.
That's cryptic.
No. Those are the bigger goals, and yes, we would love to do that. I think there's a bit of, I don't want to say hesitation, there's caution in how we use the data because these are experiments, right? I would say the number one thing I've run into when I try to develop partnerships, people have their ways of doing things. We're all creatures of habit, right? And you're gonna have to make a decision, go, no go, yes, no. You wanna be able to rely on your system. And the data that feeds into it has to be something that's consistent. It's got a long record. They wanna use that. When you have experiment, we've only been flying for 4 years, and you'd be surprised at the amount of reluctance that people have to say, yeah, this is great, this works. But we don't know if you're gonna be around a few years from now, so we don't want to change our system, adapt to something better, and then lose all that again. And that's the other thing that I did not say. We are establishing a data record. If you think about, we are providing a history of what's going on with our planet from a global perspective. And that's something that's very, very important because the longer we do this, the less convincing that argument can be that we're not around. So, but there's challenges. But absolutely, there's a desire. We actually work with the international group, which is the Global Earth Observation, and they are based in Geneva. And there are definitely people that are trying to use these observations and how can they apply them. And in fact, I would say that we are more successful. Our data being used and implemented for decision making, I would say that it's better outside of the US than it is because of the politics and the red tape that we have.
How many more do you want? One more question, sorry.
You talked about sharing the data and being able to access data. Can anyone just go to the NASA website and download the data, or how does that work?
No.
Is it like a big
You'll
zip
get
file?
lost on a NASA website. No, you can't find it. All our data is housed in what we call DACs, and DAC stands for Distributed Active Archive Centers. And there are numerous across the country, and they house the data that you're looking for. For example, OCO2 is housed at the Goddard DAC, that's in Greenbelt, Maryland. SMAP data.
Sorry, that was my bad.
Okay. Okay, SMAP data is at NSIDC, which is the National Snow and Ice Data Center in Boulder. So it just depends on what data you're looking for, and you would have to go to the DAC. We have a standard format. Our format is called HDF, which stands for Hierarchical Data Format. Anybody use it? See? And then they wonder, why aren't they using our data? Because they don't know how. And or NetCDF, that some do that. So that's the biggest challenge right now, and that's something that I'm working with different folks in trying to create products. We call them data products in that people can actually use. That's first of all gridded, because if it's not gridded, most people can't use it because it's not naturally gridded. And yeah, so just trying to get more users, but we're working on it. It's a work in progress. Thank you.